So, given this short summary, you can see there are many reactor types possible. Today, almost all of the reactors are what are called U-235 burners. Well, U-235 is only 0.7% of uranium. You can make a little bit of plutonium, roughly, it's another 0.3%. So you're only using 1%. What happens to the other 99%? This is what everybody's trying to do today. You try to throw it away, and you can't even throw it away. No country has been successful at throwing away 99%. It's kind of crazy to throw away 99%. But that is the current technology. Breeders, on the other hand, have zero waste, as we'll see. Okay? You can make use of everything that you produce. So the other is whether you moderate, whether you want to slow down the neutrons to where the cross sections are big so you don't need as much material to have a reactor. So you can slow it down. The first thing that comes in mind is use a proton. You know, it has almost the same mass as a neutron. So when they collide, in one collision, the neutron can give its energy to the hydrogen. Well, unfortunately, hydrogen also absorbs neutrons a little bit. So it's not the best moderator. A better moderator is deuterium. Why? Because that hydrogen already ate a neutron in the Big Bang. It's full. It doesn't want any more neutrons. So that's heavy water reactor. That's CANDU, what the Canadians built. Very fine reactor. Or you can use graphite. Okay? It's an accident of nature that carbon, which has two stable isotopes and one radioactive, carbon-14, none of them like neutrons. Because for astrophysical reasons, none of them were made by ROS process. Okay, they were all made by other kinds of process. And oxygen, which has three stable isotopes, none of them also like it. All others, you better choose something that only has one isotope if you don't want to eat neutrons. And the reason is because if they would like to eat a neutron, it would have ate another neutron and produced another stable isotope. So you look for things which have only one stable isotope when you want to have neutron economy. And those, for light elements, are all made not in the Big Bang, not in late stages of stellar evolution, but by cosmic rays. Spallation. Okay, so you would like to do a thermal because I will give you the lowest fuel requirement. You could scale up faster, or you can do fast, but then you need large fuel inventory. Had we started this work, back in 1943, today we would not have climate change, but it's too late for fast reactors. They cannot come line fast enough because you can't get the inventory fast enough. All right? It's unfortunate. So today, we have to use something that has better cross-section. So thermal would be best, but as we'll see, for weapons proliferation, something in the middle is better. And that graphite can do for you. Okay, what about this fuel state? Well, conventional choice is to put it as a solid. Can't go away somewhere, so you contain it as a solid. But if you're a chemist, that's the worst thing to have, a solid. It's very hard to have solid react if you need to extract things or react things. A liquid is much, much better. All right? That's a fluid of choice. So that's our choice. Okay? Coolant. Well, water comes to mind. Okay? Water is cold. After all, light water reactors were built because the US used them for submarine. If you're in a submarine, what are you going to use for coolant? It's a no-brainer. There's water all around you. It's salty water. So what? I have a nuclear reactor on board. I can distill any amount of water I need, all right? Plus give the crew something to drink. So that was a choice, historical. But it's not the best choice. Why? Because water has hydrogen in it. It's H2O. So if it touches hot metal, in particular the kind of metal that's used in solid reactors, it can generate hydrogen, which is explosive, as we saw in Fukushima. Okay? You can use helium. Helium, we all know from Big Bang theory, it's kind of a dead end for neutron capture. Okay? But it needs high operating temperature, has no neutron electron absorption. So it's all good except it's a gas. Right? So it's hard to get something very compact with helium. Or you can use liquid metal. Liquid metals are good because they have good conduction. They don't cause corrosion. One metal touching another typically doesn't cause corrosion. So they're good, and that's one of the choices. Bill Gates is building a metal reactor like this. But we choose molten salt, right? Following the lead of Oak Ridge National Lab. Why? Despite the fact that it's corrosive, it can be very compact, and more importantly, it can operate at negative gauge pressure. Gauge means relative to atmosphere. We're not talking about dark energy here. We're just talking about operating at lower pressure than atmospheric pressure. So if you have a leak, the gases blow in and don't blow out. If they blow out, you have radioactive gas somewhere you don't want. So that is so important for that reason, as well as the fact that molten salt has many interesting chemical properties that we choose to look at molten salt reactors. One fluid versus two fluids. So you can have a fluid for holding the fuel, you can have a fluid holding the blanket, or you can mix the two. It's a good idea to keep the thorium separate because they are very chemically similar to lanthanides. Lanthanides are part of this periodic table. Most people don't know, but they're part of the rare earths. Okay, and thorium behaves chemically like a rare earth. And that's why thorium is a byproduct of rare earth mining. Rare earths are used everywhere in the electronics industry. That's a huge industry. There's lots of thorium that nobody knows what to do with. China is stockpiling them, and they think this is the best reactor you can build. Okay, and this is the reason. It's dirt cheap, literally, because it has no other industrial use. And you don't need to do isotope separation because it only has one stable isotope. So I've explained why it's safe and sustainable, it's secure. So secure, how can it be superior in cost? And the answer to that is in the S diagram. So please ask me why, but I'll tell you what right now. Nuclear energy, no matter how good the reactor, is really hard for it to compete against natural gas for generating electricity. So the solution is either to kill natural gas, which is difficult, or, and maybe shouldn't be done, or not to generate turbine electricity. Do something more economically valuable. And as I'll show you now, what you should use is the heat. If you're using heat, you're a million times better than fossil fuels. If you use nuclear generated turbine electricity, you're barely better than fossil. And then all the baggage that goes with nuclear comes into making it more expensive. So that's the reason, okay? And I can explain that scientifically to you, but it would take too long. So here's the two-fluid fuel and coolant, MSBR. That's what they call it. Oak Ridge called it, molten salt breeder reactor. And a guy named Kirk Sorensen revived this thing after it was killed more than 50 years ago and renamed it as liquid fluoride thorium reactor. So often when people talk about thorium reactors, they are referring to this lifter concept of Kirk Sorensen, who was a NASA engineer, by the way. And not by MSBR, but I like the old name. I'm at that age where I like the original names. Okay, so that's what we use. And it is acknowledged by all experts as the best possible nuclear reactor if it's possible to build. Okay? So here's something that was invented 60 years ago, and we don't actually know whether it's possible to build a breeder version of this reactor. All right? Therefore, not all the intellectual property has now gone into the public domain. There are knowledge, which one can develop, and patent, and not try to control the patent, but not also allowing other people to control the patent. And I'm happy to say I hold the patent on two-fluid molten salt breeder reactors because we found enough modifications to make it doable, whereas Fermi thought it was not. Okay? So we hold the patent in the United States, in China, in Russia, and in Japan, and applying for them in other places. Okay, so how does this work? So the way you get it started is to burn up all the nuclear waste that we've stockpiled from 50 years of light water usage. What is that nuclear waste in the form of? Well, light water used spent fuel or used fuel consists mostly of U-238 that you didn't transform into plutonium. U-235 you didn't quite finish burning. So you take that out of the reactor and you give it to other people who are building integral fast reactors or lead-free reactors or the traveling wave reactor, right? That's what Bill Gates is trying to do. But as I said, that will certainly help, but it's probably a little too late to solve climate change for that. So you're left with the plutonium after you've extracted up uranium and the other stuff. That stuff I said was a big mess up there. It's called generically actinides or sometimes transuranics, okay, together. So you use a process called pyroprocessing to separate that from everything else and put it into the core of a reactor, whose basic component is spherical in shape and is graphitic in nature. You're left with fission products, and there are lots of them. That's why the reactor stopped. You generated so many fission products, they absorbed more neutrons, you couldn't even sustain the chain reaction. So what do you do with those fission products? After you've separated them, you've gotten rid of the tough things that have very long lifetimes. These things have half-lives of 30 years or less. So if you bury it underground for 10 half-lives, they go below background. So burying something for 300 years is not difficult. Okay? The Chinese 4,000 years ago knew how to bury things so that 4,000 years later you can recover them. So 300 years, I'd be willing to do it in my backyard. Okay? But you shouldn't do that. There's good stuff in here. What are some of these good stuff? And they should be regulated use. There are things that could be used for nuclear medicine. There are things that could be used for nuclear batteries. For example, plutonium-238 is used to allow us to go to Pluto. It allowed us to go to Galileo, to the outer planets, okay? Allowed us to have a Mars rover. Strontium-90 is another thing. Nuclear battery. These are batteries. It's not like this thing, which if I unplug it, will go dead after a few hours. Okay? This thing will last 80 years. All right? It won't go dead. So if wherever you have a light that cannot fail, don't use chemical batteries. That's not a chemical battery. That's tritium powering that. All right? So if you have lighthouses in the Arctic, as the Russians have, they power with strontium-90. All right? Lasts for decades. You have to use it. Those of you who like Lord of the Rings, that's my theory of what Galadriel's file is. A light, right, to use when all other lights go out. It's a nuclear battery. Okay, so what is in here? So the blanket salt is actually in a big pool. That's one of the things why I was able to get a patent, which contains thorium in the form of a salt, thorium fluoride, F4. And that's the only valent state for thorium, so you can't add any more fluorines or remove them easily. The carrier salt, the thing that you dissolve it in, the solvent, is conventionally, historically, lithium fluoride, beryllium fluoride. But lithium violates this rule. It has two stable isotopes, lithium-6 and lithium-7. 6 is made in spallation reaction. 7 is made mostly in the Big Bang. When the Big Bang tried to make lithium-6, it immediately ate another neutron to become lithium-7. All right? So lithium-6 you cannot allow in a nuclear reactor. So you have to separate it out. You have to do isotope separation. there's no reason for anybody else to do isotope separation. So why would they do it? They want to wait until you get it. But you can't do any nuclear reactors until somebody has done the isotope separation. So we think this is a hopeless thing until you demonstrate it's really worthwhile to do it. So we use sodium fluoride, beryllium fluoride. Beryllium has only one isotope, 9, made by cosmic ray spallation. Sodium has only one stable isotope, 23. That's why people use it in, Bill Gates wants to use it in fast reactors. So it's sodium fluoride, beryllium fluoride. So then the question is, can you dissolve enough of the fuel or the